Hello, good evening. Can you hear me?
Yes,
Yeah, I see Professor
I
Sukumar
think,
is. Good evening, Professor Sukumar.
good evening.
So we have students. I think we are at 6:03. At
Okay.
6:08, another 5 minutes, we can start. We have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 6. So we have around 50 people
46.
in the
It
meeting.
says at the bottom, 46.
46. Yeah. Okay, so let's
Yeah,
wait for.
it says at the bottom, 48.
Yeah, so
Sure.
let's wait for 4 more minutes. 6:08 we'll get started. I'll turn off my camera and my mic. So let me just introduce Professor Sukumar. Professor Sukumar has worn several hats. Um, sort of, I think, partly has led to my appreciation of him and friendship. We've even previously published his book on drug discovery. I'll sort of start retro, uh, sort of chronologically. He's currently mentor of School of Bioinformatics Biotechnology at Amrita, visiting professor there. Before that, he was at Shiv Nadar. He's been at various positions in India, including IIT Madras. He has been a Humboldt Fellow in Germany. He did his PhD from Stony Brook in US, um, New York State. He has even shifted from quantum chemistry to drug discovery and computer-aided drug design. He was pioneer of that in India. He was one of the first to publish papers on using computers, using these approaches of docking and all that, chemi-informatics approaches to publish papers on drug discovery. And we are very honored to have him as one of the mentors in the project. And it's a privilege to have him deliver a lecture on scientific writing. Over to you, Professor Sukumar.
Okay, good evening, everyone. Uh, Thanks for the invitation and thanks to all of you for being here. Um, just a small correction. I'm actually in the School of AI here at Amrita. Okay, so I'm in the School of Artificial Intelligence. But yeah, I'm doing basically the things that you. Um, okay, so you've been having several talks, listening to several talks on scientific writing, and I expect will have got a good perspective on what it takes to write a scientific paper, including what it takes to to finalize a project and what I will talk to you to today will be more on how do you recognize good science and how do you recognize bad science. Okay, so let me uh, load my presentation. Okay, that's okay. Now, mute website. Can everyone see my screen?
Yes.
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 Okay.
no, sir.
Okay.
No,
So,
sir. Sir, I can't see your screen.
I I think some said yes, some said no. So maybe it's just a maybe it's just a network issue. Yeah. So it's possibly just a network issue, and it'll come when you. Okay. Can we mute the others? Okay. So so these are some of the topics I'll be going through today. So basically, I'll start off on a very philosophical note, but then I'll get down to the scientific literature and how do you critically analyze the scientific literature, sift through the junk from the non-junk. And believe me, there's a lot of junk out there. And then finally, we'll get down to some hard statistics. But that'll be right at the end, so it will not be a very heavy. It will not be a very technically heavy presentation. Okay. So first, what do we? So when you write your discussion in a paper, when you write your abstract, when you write your conclusions, you're focusing on the explanation of the results that you have generated. Okay, so what constitutes an explanation? Okay, now this is actually different in different fields. So the explanation in physics, chemistry, biology, and mathematics is quite different. In mathematics, it is deductive logic. In most other sciences, what we use is inductive logic, not deductive logic. So that means you don't prove from an axiom, starting from an axiom, you don't prove a theorem in biology, but from a series of observations, you generalize. Okay, so that's called inductive logic. In chemistry, multiple levels of explanation are possible. You can do a phenomenological explanation, or you can do a reductionist explanation. And the same thing in molecular biology. In biology, if you reducing something to molecular biology, that's a reductionist explanation. But if you're staying in a phenomenological level, then that's a different level of explanation. Now, biology often deals with why questions, but actually these are disguised how questions. In physics, we don't talk about, let's say, why the universe is the way it is, but we talk about how the universe got to be the way it is. In biology, we often talk about why, that is the purpose of a particular adaptation, the function of a particular gene, but we should recognize that these are actually disguised how questions. At the molecular level, the gene doesn't have a purpose. The molecule doesn't have a purpose. It just interacts. Okay, it just interacts. The function is just a consequence of the physics of it. So, okay. So evolution is often framed as a why question, but it's actually not so. It's not that the organisms evolved in order to get better. The molecules basically, those molecules survived, essentially got eliminated from the population, and therefore what was left eventually progressively got fitter in given that set of circumstances. When the circumstances changed, maybe those organisms vanished and new organisms came up. So it's not what we call adaptability. So the molecular biology gives us the how behind the why. And here the famous or the well-known quotation is that nothing in biology makes sense except in the light of natural selection. So that provides the ultimate explanation for most phenomena in biology. Okay, so when we talk about inductive logic, so when we design an experiment, we design an experiment to verify we should design experiments in order to disprove a hypothesis. Okay? So Karl Popper realized that no potentially. I think I briefly lost my connection. But can everybody hear me right now? Okay. I was talking about falsifiability. Are you seeing my slide now, or I need to reshare it? Let me reshare it. Okay. Yeah. Okay. So, so Popper's view was that what we are doing is actually trying to prove a hypothesis, try to rule out possibilities. Okay, so you never prove your theory like you would in mathematics. Prove a theorem. You never prove your hypothesis. You eliminate other competing hypotheses. And therefore, in the words of Sherlock Holmes and other novels, when you eliminate the impossible, what is left, however improbable, has to be true. Okay, so you eliminate those which eliminate competing hypotheses, then what you most likely true until you find something else. Okay, so no amount of data can really prove a theory, but even a single key data point can potentially disprove it. In other words, for any hypothesis to aspire to the status of a scientific theory, it has to be inherently disprovable or falsifiable. So this is what I meant falsifiability. Okay, it doesn't mean that it has to be false, but it has to be falsifiable. You cannot have a theory which can never be disproved. If you have something like that, just an assertion. Okay, that's not a theory. So no theory is completely correct. It's not falsifiable. It can be accepted. No outcomes at the level of experimental testing can confirm a scientific theory, but a single counterexample is logically decisive. And here, if theory that there are no black swans, all swans are white. So this is your hypothesis, all swans are white. You can go out and then observe 100 swans, 1,000 swans, 10,000 swans, a million swans, and they're all white. You have confidence in your hypothesis that okay, swans are bright. But that doesn't mean that the hypothesis is proven. Okay? It's intuitively accepted. The day you find black swan, the day you see a black swan, your hypothesis is proven. So even one data point, which is one reliable data point, it can't be a white swan with somebody has painted black, or a swan in a shadow or something like that. But one reliable data point, a black swan, which proves the hypothesis that all swans are white. Okay. So according to Popper, a theory should be scientific if it is falsifiable. So falsifiability is useful to any theory that is definitely realistic. Any theory will be falsified when more experimental data or resources become available. So that's why you see people even going out and performing tests of Einstein's theory of general relativity, algorithms. Time and over 100 years have all been consistent with general relativity, but still new experiments in new domains, new ranges of parameters can be used to test the theory. Science does progress by experimental testing, conjectures, and refutations. and only the fittest theory survived and tentatively and temporarily accepted. Okay, again, so again, survival of the fittest. But we're talking about theories here. A theory can never necessarily be completely true. It can only be said that it is the best available in the sense that it is better than any of the alternatives. So, as I said, if you rule out all the impossibles, then what is left is accepted. Okay, for the time being. So scientific knowledge is always tentative. So here we point out difference between ontology and epistemology. Ontology is the philosophical study of the nature of being becoming existence reality, or in other words, how things really are. Okay. So you assume that there is something called objective reality and know some part of it. Okay, so that's what we are trying to keep on improving our knowledge so that it gets closer to the objective reality. So the ontology describes that objective, the nature of objective reality. But epistemology is concerned with the nature of scope of knowledge. That is how we know what we know, how we collect the evidence. And also, of course, this was looking out of detractors. While Popper was heavily influenced by his training in physics, in proposing his qualification hypothesis, Roald Nobel Prize in chemistry, he has argued basically that falsification is almost irrelevant to many chemists whose main activity is to synthesize molecules. That's what chemists do. They make molecules, right? So yes, what hypothesis is very falsifying when you make a new molecule, when you make a new drug to treat cancer, or a new polymer to test toxic environmental chemicals. So you make this molecule, what hypothesis are you falsifying? But perhaps we should really call this we should call this molecular engineering, making molecular engineering, making a polymer. But we are testing, for instance, we are testing the hypothesis of the mechanism of action of drug. When you make
Let me see what is the status of Dr. Sukumar. I will call him and then join. And if the problem persons, we will record a session with him and upload it or invest separately. Okay, let me just give it a try.
I think I'm again that I'm back now. So can you? So at what point did I go off? At what point did I go off?
We became somewhat saying basically we were explaining the difference between deduction and induction, right? Explanative logic as well as argument can never get to you kind of explain that back on. That's where you were at.
Okay.
And then
Did we go through this Thomas More's ideas?
No.
Did we go through this? No.
When I mean, you can start here.
Okay. So, according to Kuhn, science goes through three distinct phases. One is normal science, where most scientists are working and they're not engaged in testing or challenging the hypothesis. So this is what chemists are doing when they make molecules. But then when the molecules that they make fail to validate their hypothesis, that's when you end up with a crisis. Not just one failed experiment, but when multiple experiments, repeated experiments across different labs fail, then that it leads to a crisis in the scientific in the existing paradigm, right? So then to solve that crisis, then we have to propose a new mechanism, a new paradigm. Okay. So and then the new paradigm accumulates evidence in support of it, and then it gains acceptance in the scientific community and supplants the old paradigm, and then we go back to normal science under the new paradigm. Okay. So I taught the logical fallacy. This Proctor Hawk, which means that it's a logical fallacy in which two events occur simultaneously. A happens when A and B happen at the same time, and therefore you conclude that A must be causing B to happen. In other words, correlation does not imply causation. As most biologists are familiar with this, correlation does not imply causation. Example being, the rooster crows every morning at sunrise, and therefore if we conclude that the rooster causes the sun to come up, that's a fallacy. Hospitals are full of sick people. Therefore, if we conclude that hospitals are making people sick, that's again a logical fallacy. Sometimes hospitals make people sick because of spread of infection, but that's not why hospitals are full of sick people. Hospitals are full of sick people because sick people go to hospitals in order to get better. If you conclude that he sometimes behaves violently when I'm around him, and use I don't know what it is that I'm doing to make him become so violent. I don't know what it is that I'm doing that somebody that I got sexually harassed. Maybe it's so clothes that I'm wearing. Maybe I went out late at night. Okay, but that's not your fault. It's the fault of the person who was harassing you. Okay, that person doesn't have any morals. Okay, so you shouldn't blame yourself for that. Next logical fallacy is post hoc ergo propter hoc. That means since Y follows event X, therefore event X must have event X must have caused event Y. Okay. So example of this was I switched from whole milk to 2% milk, and my son scored an A on his last test after scoring C's all year. Okay. There's no relation between the kind of milk that you consume and the run. Logical even though even followed the other. A tenant moves into an apartment and the building's furnace goes faulty. The manager blames the tenant's arrival for the malfunction. Again, logical fallacy. This is the post hoc ergo propter hoc fallacy. Here's another logical fallacy with footballer Pele. And you can read what it says. They blame the dip in his performance on a fan who gave him a specific shirt. Then after getting the shirt back, his performance recovered. But then he found that the shirt returned was not the original shirt at all. Okay. So here I now talk about what Irving Langmuir characterized as pathological science. I don't mean the science of pathology, but what he meant was the science itself is diseased. Okay, the science itself is unreliable. So this was coined by Nobel laureate in chemistry Irving Langmuir. In his presentation, he made at General Electric's for laboratory. He described his thinking session as barely detectable causal agents observed near the threshold of sensation, which are nevertheless asserted to have been detected with great accuracy. The supporters offer fantastic theories that are contrary to experience and meet criticisms with ad hoc hypotheses, ad hoc excuses, and most tellingly, only the supporters can reproduce the results. Critics often can't duplicate the results. These are cases where there is no dishonesty involved, but when people are tricked into false results by a lack of understanding about what human beings can do to themselves in the way of being led astray by subjective effects, wishful thinking, and threshold interactions. So we'll try to distinguish here between wishful thinking, intentional fraud, and this kind of pathological effects. So when you're not talking about intentional fraud, when you're by wishful thinking, then example sign of this instances have attracted a great deal of attention. Sometimes hundreds of papers have been published on them. Sometimes it has lasted for 15 or 20 years and then gradually have died away. I'll give you a few examples. But before that, this is Langmuir's invented gas-filled and incandescent electric lamp, Langmuir probe, hydrogen welding technique, got a Nobel Prize in chemistry for his work in 1932. So these are the symptoms that he gave for pathological science. The maximum effect that is observed is produced by a causative agent of barely detectable intensity, and the magnitude of the effect is substantially independent of the intensity of the cause. The effect is of a magnitude that remains close to detectability. This is the low statistical significance of the results. We'll talk about statistical significance right at the end. Theories outside of the field's paradigm are suggested, so we are basically proposing outlandish theories. Criticisms are met by ad hoc excuses thought up on the spur of the moment. The report takes falls off oblivion. The remarkable result is specific for only a special system. So it works only in some cases, it doesn't work in all cases. Some special technique or equipment is involved. You only get this if you do it in my apparatus, it doesn't work if you do it in your apparatus. So things like this. The result requires a stunning departure from the paradigms that fully determine results in all other comparable systems, including those studied by the authors. So you see here that there is a thin line between this and what Thomas Kuhn described as a paradigm shift. Sometimes this could be a genuine phenomenon where the results the results do call for a paradigm shift. But if all of these other or many of these other things are true, then you start suspecting it, that it's actually pathological science and not really a genuine phenomenon which requires a paradigm shift. Okay, so okay, so let me present again. Okay, is it visible now? Okay, so these were some of the symptoms of pathological science that he proposed. So I will share this with Dr. Khurana, the presentation at the end, so that, or anyway, you have the thing. So, so whatever didn't show up on the video, you can check it against the slides. So you can actually find this article which he wrote. Actually, it was written posthumously in 1989. This was a colloquium, but it's based on a colloquium given by Irving Langmuir in 1953. Okay, so you can find it in the link. So let me just give some examples. I will not read all of this, but there was the example of polywater. So these people proposed that water actually polymerizes and gives rise to a new material under certain circumstances, which has very different properties from normal water. Okay, that it has a higher density than normal, viscosity 15 times that of normal water, boiling point higher than 100 degrees centigrade, freezing point lower than 0, and so forth. So for the next several years, on this system, and all, some people even made catastrophic predictions that if this polywater escaped from the lab, it could auto-catalyze and polymerize all the world's water. then the case crumbled. More and more people failed to reproduce these results, and eventually the scientists who had described the phenomenon admitted that it did not exist. But often that doesn't happen. Often the people who proposed it go to their graves still arguing that it is true. Another example is cold fusion, which is proposed by Pons and Fleischmann at the University of Utah. They claim to have developed nuclear fusion on their desktop, basically in a flask in a test tube. And hundreds of experimental and theoretical papers followed, including some of my friends who wrote theories from around the world. But few people were able to reproduce the results, and most of those could not. Most of those results could be explained by other phenomena, for example, cosmic their equipment from cosmic rays, and that was what is causing the heating that was observed. And today we hardly hear about cold fusion. Then there's the Jacques Benveniste's infinite dilution studies. So this is basically taking on the theory of homeopathy, that you can dilute a drug many times, so that eventually your sample in your test tube has diluted so much that there is an average no molecule of water in it. But it is giving rise to a therapeutic effect. And he claims to have showed this experimentally. He published a paper on it, and then there were others who disputed that. The attempts to replicate this work failed. So Nature, to whom the Nature magazine to whom these papers had been sent, they sent a team to investigate. So the editor of Nature, John Maddox, the magician James Randi, and a chemist, they went to investigate. The chemist looked at all the lab records and all that and found that the lab records were not properly kept. Others found that there was possible sample contamination, conflicting measurements, statistics had been massaged. So nowadays we use double-blind experiments to test something like this, so that the experimenter who experiment doesn't know whether the sample he's using is actually a drug or a placebo, and the patient who receives it also doesn't know whether it's a drug or a placebo. Okay, so this is the gold standard that is used nowadays. Okay, so we talked about ad hoc hypotheses that people use in order to explain things. This has been common in ESP research, extrasensory perception. People claim that the researchers' thoughts are influencing the pointer reading. So Helmut Schmidt put cockroaches in a box where they could give themselves electric shocks. So you would assume that cockroaches don't like to be shocked and they would avoid it. But he found that and the cockroaches would then learn from experience and stop giving themselves shocks. But the cockroaches actually gave themselves more shocks than predicted by chance. And he concluded, so this was the ad hoc hypothesis, that because he hated cockroaches, it is a psychokinetic effect. It influenced the cockroaches, influenced the random cell, and make that his psychokinetic effect made the cockroaches shock themselves. Okay, so it's always more reasonable to apply Occam's razor than to offer this kind of ad hoc hypothesis. So Occam's razor is basically means plurality should not be posited without necessity. So this is proposed by William of Occam, English Franciscan friar, philosopher, and theologian. It states that among competing hypotheses, the one with the fewest assumptions should be selected. Also called the principle of parsimony, which can also be interpreted to mean the simpler the explanation, the better, or don't multiply hypotheses unnecessarily. For data modelers, we interpret that as saying that simpler models are better. But of course, remember Einstein's caution that all models should be as simple as possible, but no simpler. That means it cannot be so simple that it fails to explain the data. Okay, it should explain all the data, but if there are two theories which both explain all the data, then the simpler one is to be preferred. Okay, so so we talked about ad hoc hypothesis, wishful thinking. Right, wishful thinking is interpreting facts, reports, events, perceptions according to what one would like to be the case rather than the actual evidence. Right, you want your experiment to succeed. You want to, if you're proposing a new something new, you want that to be successful, right? You don't want it to fail. So there's a tendency to try to interpret adverse findings and say, okay, something happened there, so that's why it's not correct. And even a small pointer reading, you say, that's positive, or a faint spot on a gel, you say, yes, that's a spot. So if it is done intentionally and without regard for the truth, then it's misinterpretation, falsification, or perversion of the truth. But when it happens without conscious intent to deceive, because we're emotionally attached to our hypothesis, then it's called wishful thinking. So here are some cases, and I'll let you decide whether it's fraud or wishful thinking. These are some stories from you might not have, most of you probably may not have heard of these, but probably Sukant might be aware of these. So there was a guy called Ramar Pillai in Tamil Nadu who claimed to have made petrol out of herbs. Okay, and he actually came to IIT Madras and he did a demonstration in front of the chief minister, who was Karunanidhi at that time, and the scientists present could not catch what they're saying. They could not find fault with what, but asked him to come back and repeat under controlled conditions. And when they did that, they found out that he was actually using a trick device. He was using a stirrer in which there was a concealed compartment in which there was petrol. Okay, so the petrol was actually not coming from the herbs, but it was concealed in the stirrer, and he had a secret lever which he opened, and so it filled up with petrol. So when he did the experiment first time, he took these herbs and then he stirred them with water, took the herbs and water and stirred them, and suddenly the smell of petrol filled the room. And he even put that petrol in a scooter and drove that scooter a short distance. So people were very, very surprised, very shocked at this. But then when he did this under controlled conditions, said, use my stirrer, use my beaker, and use your same herbs and water, but use my stirrer, and then he couldn't reproduce it. And then they found out that he was using this magician trick. There was a one-day wonder, I think, in the 90s when Ganesh statues started drinking milk, and this news spread within hours. And this was pre-internet days, but through phone calls, and it spread across the country and even spread to America. And people rushed to their nearest temple and started pouring milk on top of Ganesh. And they were thinking, saying that Ganesh is drinking the milk. Most of the milk was draining, or all the milk was draining, but they could see most of the milk draining. Some of it was maybe going into cracks which they couldn't see, and so they interpreted that as saying that Ganesh is drinking milk. Recently, there were people claimed that there was immunity to COVID-19 by eating gobar. Okay, you can find these at this article. More recently, there's this researcher called Ranga Diaz from University of Rochester. He has reported room temperature superconductivity. He published in Nature, but it was retracted in 2022. His group published 2 papers claiming to have achieved high temperature superconductivity, but these were retracted by Nature when they found that there was possible evidence of fraud, and then the university is now investigating it. So the paper was controversial, faced scrutiny due to concerns about data availability, data analysis methods, lack of reproducibility, studies recipe being vague and incomplete, the way the group measured the material's magnetic behavior. So these are all things that you can actually, when you look at a paper, these are checkpoints which you should see. Are the data available? Have the researchers made data available? Earlier, this was not very common, but nowadays most journals insist that data should be made available. But if people haven't made the data available, then it should raise some suspicion for you. What are the analysis methods that they use? Did they use standard methods, or do they invent their own methods? Okay. Lack of reproducibility. Are you able to reproduce it? Are other labs able to reproduce it? Has the protocol been specified, have been described in detail, or is it just described very vaguely? Okay, so that prevents people from actually trying to reproducing it correctly. Objections, and an independent group of scientists was commissioned by the University of Rochester. They concluded that Diaz had committed scientific misconduct, including fabrication, falsification, plagiarism. But Diaz and his co-authors, they have founded a company in order to pursue commercial room temperature superconductors, and he continues to claim that this is a real phenomenon. Okay, so there are many such instances. You can find many more instances in this paper, and there's been a lot of retractions due to fraud in the scientific literature. There's this thing, cow exam, which you might have heard about, national cow exam, and which was created a lot of controversy, and then it was postponed after allegations of claim and pseudoscience. Exams to be conducted but the syllabus sparked controversy because there was it contained unscientific claims namely that cow milk has traces of gold in it, that earthquakes occur due to cow slaughter, and so forth. Even recently, the director of IIT Mandi has claimed that slaughter of animals causes earthquakes and landslides. Okay, so I told you that there's a lot of retractions and very low reproducibility, but in some fields, particularly in biomedical research, Ioannidis and has found that there's most published research findings in the biomedical field are false, and the probability of that the claim is true depends upon the study power and bias, the number of other studies, the rate of true to true relationships, true relationships to no relationships among the relationships probed, and the research finding is less likely when the studies conducted in the field are smaller. So that's why, small sample sizes, right? So when you have small sample sizes, statistical anomalies can get magnified. So therefore, you try to collect as much data as you can. When the effect sizes are smaller, okay, if you're looking at a pointer reading, there's a very small deflection. If you're looking at a spot on a gel, there's a very faint spot. So the effect size is very small. When there is very little difference between two channels in the gel. Then when there is greater flexibility in design, definitions, and outcomes, that means when the protocol has not been well specified, people can design their experiments whichever way they feel like, or whichever way makes the results come out the way they want them to. Okay, if people are doing that, then the research finding is less likely to be true. When there is greater financial and other interest and prejudice. Okay, so if people have a financial stake in the results, they are more likely to fudge it. Okay, when more teams are competing in a hot scientific field, right? When there's a lot of prestige in people competing, pressure to try to get results, to try to get revolutionary results like Ranga Diaz and claim that there's a paradigm shift. Okay, so there's okay, I will skip this, but this is basically Bayes' theorem, which you might have seen in your probability and statistics course, which is basically the conditional probability. So this P of A, this left hand side is the conditional probability of A happening event A given that B has happened. P, this is the sorry, let me put the pointer. Let's see. Okay, can you see my pointer or? Okay. On the right hand side, we have the conditional probability of B given A times the prior probability of A divided by the prior probability of B. So prior probability of A and B, it refers to the probability of A if you know nothing about B, or the probability of B if you know nothing about A. And you can easily prove this theorem because the conditional probability times the prior probability gives you what is called the joint probability, the probability that both A and B are true. Okay, the probability of both A and B happening. And that is both left hand side and the right hand side gives you this joint probability. Now, if you divide that by P of B, then you get with Bayes' theorem. Okay, so why am I saying this? So these are some examples which, if you're not familiar with Bayes' rule, you can go through some of these examples. For instance, a patient exhibits fever and chills, and a doctor suspects tuberculosis but would like to know the conditional probability that the patient has tuberculosis given the results. So what you're given is that approximately half of all TB sufferers exhibit these symptoms at any point, which means that P of fever and chills given TB is equal to 0.5. Then tuberculosis is now rare and affects some 0.01% of the population. In other words, the P of tuberculosis is 0.0001. Okay, 0.001% means 0.001. And fever is a common symptom generated by hundreds of diseases and affecting 3% of the population every year. So that means the probability of fever and chills equal to 0.03. So putting that, applying Bayes' rule, then we get the conditional probability of TB given fever and chills is 0.5 times 0.0001 divided by 0.03, which is 0.001667. Okay, so and so similarly, a patient has a blood test done for lupus. The test comes back positive, but the test is known to give a false positive in 2% cases. In patients with lupus, the test is 99% positive, and we know that lupus is half of the population. The doctor wants to know the condition of the patient has lupus. And when you go to the test, when you go to the math, you find that the probability of lupus given the positive test result is actually only 0.199. That means only, so even though the test comes back positive, the probability that you have lupus is only 20%. Okay, and that's because it's a rare disease, and so so you have to work in the priors. So when you apply this to theories, you get something called a probability that a research finding is true, positive prior probability. Then the P of B is now the statistical probability of the study yielding the positive result. P of A is the prior probability that the research findings is true. Okay, and when INET is applied that to these results, they found that the probability that a research finding is true is a function of the pre-study odds for various levels of bias, and it is a function of the pre-study odds for various numbers of conducted cases. So corollaries of this are that the smaller the studies in a scientific field, the less likely the research findings are to be true. The smaller the effect sizes in a scientific field, the less likely the research findings are to be true. The greater the number and the fewer the selection of tested relationships in a scientific field, the less likely the research findings are to be true. The greater the flexibility in design, definition, outcome, and analytical modes in a scientific field, the less likely they are to be true. The greater the financial and other interests and prejudices, the less likely they are to be true. And the hotter the scientific field, the less likely they are to be true. Okay, so there's a measure which is called surprisal, which has been employed to of an idea. Okay, and it's a function of the hotness of the field, the high gain and the high risk. Okay, but I will not. You can follow this link if you want to know more about that. I will not go into details about that. Before I conclude with the statistics portion, I'll just tell you a little bit about why we feel and why we are influenced like this. So these are insights from neuroscience, okay, as to why your mind works the way it does. Hello? Okay. We store memories differently based on how they were experienced. Okay, that means that an emotional memory is recorded and stored differently than something which you just try to mug up. Okay, we reduce events and lists to their key elements. We discard specifics to form generalities. Okay, this is, as you saw, this is the basis of scientific induction. This is why science works. We generalize from many observations and make a general theory. So this is actually good, but it can also fool us. We tend to form biases as a result of this. We try to form biases that some people are like this based on their color, based on their ethnicity, based on their caste, based on their religion. We tend to make generalizations of about people based on their level of, based on their wealth, based upon their level of education. We again form a lot of generalizations about people. Okay, we edit and reinforce some memories after the fact. Or memories are they're not like data entered into a hard drive of a computer. They are neural connections which are continuously being reinforced. Unlike an artificial neural network or brains, there is no separate training epoch and a testing epoch. Each time we recall a fact, we are actually editing some of that memory. Each time we recall a memory, we are actually reinforcing it and editing it. So strengthening some aspects and weakening some other aspects of the memory. We notice things. So this is why memory is an unreliable guide to, and this has now been recognized even in courts of law, that eyewitness testimony is not always very reliable because of this, the tricks that our memory plays on us. We notice things that are already primed in memory are repeated often. So our biases affect how we notice. We notice things that try to confirm our beliefs. If you see people arguing on social media, you will find that people rarely change their minds. They just, they use the data in order to reinforce their prior assumptions. Okay. Bizarre, funny, or visually striking events stick out more than commonplace, unfunny ones. We notice when something has changed, that is trends. Okay. And there are evolutionary reasons for this. If you look at a cat, the cat might seem to be sleeping, but if you suddenly drag something at the edge of the room, or if a mouse scurries across the edge of the room, suddenly the cat is all attention and jumps at it. So the the visual cortex of the cat is trying to detect motion. Okay. Similarly, time detects motion, change. Okay, these have been important for our evolutionary survival. If we see a motion in the forest, something, a snake or a tiger, if we didn't run away from it, or our ancestors, if they didn't run away from it, they would have died, and we wouldn't be here to tell the story. So the fact that we survived, that we are here, means that our ancestors were noticing these changes, and those who noticed these changes were the ones who survived. So we are drawn to details that confirm our existing beliefs. This is called confirmation bias. Lily talked about this, right? We tend to reinforce our existing biases. We notice flaws in others more easily than in ourselves. We imagine the things and people we are familiar with are fond of us, that we are fond of, as better. And as I said, we edit and reinforce some memories after the fact, cognitive bias. We favor simplistic options over complex, ambiguous ones. To avoid mistakes, we try to avoid irreversible decisions. We tend to complete things we have invested time and energy in. So often you'll find yourself doing stupid things when you should be doing more important things, but you're doing those stupid things just because you want to complete it, even though it's not important. We favor the immediate task in front of us. We tend to find stories and patterns even when looking at sparse data. Okay, the human brain is amazingly adapted for pattern recognition. We fill in characteristics from stereotypes, generalities, and prior history, generalization. So as I said, this is the basis of inductive logic. We simplify probabilities and numbers to make them easier to think about. And we think we know what other people are thinking. Okay. So with this, I'll skip to the final thing. So null hypothesis. So I'll skip to this statistics portion. So null hypothesis requires constructing what data would be like, given that chance or random processes were responsible for the results. The hypothesis that chance alone is responsible for the results is called the null hypothesis. The model of the result of the random process is called the distribution under the null hypothesis. The obtained results are then compared with the distribution under the null hypothesis, and the likelihood of finding the obtained results is thereby determined. So this is the hypothesis testing theory of Ronald Fisher. In the significance testing approach, a null hypothesis is rejected if the observed data are significantly unlikely to have occurred if the null hypothesis is true. So the null hypothesis is rejected, and an alternate hypothesis is accepted in its place. So he says you should always compare your hypothesis with the null hypothesis. Null hypothesis means, like for instance, placebo. The cure that you're seeing, the improvement that you're seeing in the patient is a result of a placebo. That would be a null hypothesis. Okay. If the data are consistent with the null hypothesis, then you cannot reject the null hypothesis and claim that the drug is causing the effect. Okay, so you have to accept the null hypothesis. That doesn't mean null hypothesis is true. That doesn't mean your drug is not effective, but you have just not been able to prove that your drug is not effective. Okay. In neither case is the null hypothesis or its alternative proven. The null hypothesis is tested with the data, and a decision is made based on how likely or unlikely the data are. As opposed to this, there was Jerzy Neumann's approach, where the null hypothesis is contrasted to an alternate hypothesis, and the two hypotheses are distinguished on the basis of data with certain error rates. Okay, so hypothesis testing involves a null hypothesis and the alternate hypothesis, accept or rejecting the null hypothesis. The odds of the null hypothesis after obtaining the data is equal to the odds of the null hypothesis before obtaining the data times the Bayes factor. So here again the Bayes theorem comes in. So choosing an appropriate and relevant null hypothesis is thus of crucial importance. Okay, so just this, yeah. So this is basically the binomial distribution, which gives you the probability distribution of a random variable, okay, with probability p. And you see that if you're tossing one dice, you get the top row. If you're tossing two dice, the distribution like this. If you're tossing three dice, okay, so you have this. In the end, if you toss a large number of dice, you get a binomial distribution, a Gaussian kind of curve. So the probability of a given number of events occurring in a fixed interval of time is known independent with a known average rate and independently of the time since the last event. The Poisson distribution is the limiting case of the binomial distribution as the number of data points goes to infinity and the probability gets small. Okay, so this is the Poisson distribution, and this is the cumulative distribution. That means if you add the data, all the data up point, or integrate all the data to the point, like this cumulative distribution. Okay, so the Gaussian distribution, which is named after Carl Friedrich Gauss, that's given by this probability distribution. So this shows the Gaussian distribution for various mean with mu in the different curves and various sigma, which is the standard deviation. Okay, so you're familiar with this, and if you integrate all the data from the minus infinity up to a certain point, you get this the cumulative distribution. Okay, that's what you get in the lower curve. Again, you have for the different mean and the different standard deviations, we have the different curves. Okay, so for the normal distribution, what is the probability that the data lie within one standard deviation of the mean? That's actually 68%. 68% of the data lie within one standard deviation of the mean. 95% of the data lie within two standard deviations of the mean. 99.8%, 99.7% of the data lie within three standard deviations of the mean. Okay, so and you can see this here. This is the central limit theorem. As the number n increases, you can see that this approximates the Gaussian distribution. The large number it approximates the Gaussian distribution. Okay, and this assumes that there are independent and identically distributed random variables with the same zero mean and same variance sigma. Okay, so then you get this these curves. Okay, and you can see that tossing various dice. So the dice has 6 sides. So if you toss one dice, each of those 6 sides has equal probability of 1/6, and you get the curve at the top left, n equal to 1. If you toss 2 dice, then you get this next curve below the green histogram, n equal to 2, n equal to 3, n equal to 4. You get the red histogram, the one on the top right, and so forth. If you toss a large number of dice, you get this Gaussian curve in the bottom right, which is the smooth profiles of the previous graph, rescaled and superimposed. Okay, so if you can compare these with the so this is now the cumulative distribution, which I showed here. That if you add up these, you get the cumulative distribution. So you see so this is what is used for hypothesis testing. Okay, and This is commonly used in industry. I will just conclude in a couple of minutes. Six Sigma is a standard which is used in industry, in many industrial sectors to improve the quality of output. That means that the data should, any data which lie more than 6 sigma outside, 6 standard deviations, you throw them out. They are considered unacceptable. If you want something of a certain thickness, of a certain width, then that's what you do. So this is the graph of the normal distribution for different mean and standard deviation. So what is the probability that a particular curve has the same mean as another curve, or two curves have different means, like shown here, the three here, different means. What they belong to the same data. They belong. So these can be actually verified by looking at the statistics. Okay. So for that, we do use certain characteristics to design experiments. Homogeneity, systematic errors should be excluded. So homogeneity means that the method of testing and precision of instrument should be the same. Systematic errors should be excluded. Standard values for comparison. Control tests must be performed. And either you choose a random sample or you choose a representative sample. Okay. So that depends on what you're listening, and the sample size should be large enough. Okay, so the procedure for testing this hypothesis is basically this t value, t distribution. You calculate this t distribution, the mean value of the sample for the mean value, which is x bar for n and variance s squared, is compared to the mean value mu for a normally distributed data. So the null hypothesis is difference between the two is only random. It's by chance. Okay, so you compare that with the null hypothesis, and you will reject you will accept the null hypothesis if this t value is less than the tabulated value of the t distribution for f equal to n minus 1, which is given here. So this was proposed by William C. Gossett. Okay, and this is the two-tailed distribution. Okay, so this is the one and two-tailed distribution. So let me conclude with telling you a little bit about William C. Gossett. So Gossett was the head experimental brewer at Guinness Laboratory. He's a pioneer in modern statistics. So unlike Ronald Fisher, who was a professor, an academic, Gossett was a chemist at the Guinness Brewery. So he pioneered a small sample experimental design and analysis with an economic approach to the theory of economic approach to the logic of uncertainty. Fisher actually rejected this economic approach, but we'll see here what is the advantage of economic approach. So what is this economic approach? So as head brewer, he was concerned with how much alcohol should beer ideally contain. So each year, depending upon the sunshine, depending upon the rain, the amount of alcohol in the crops is going to be different. So now when you brew that and make beer and finally sell it to the shops, sell it to the bars, if there is too little alcohol in the beer, then the beer has a flat taste and it will not sell very well. People won't buy it, and that results in low profit for the company. If there is too much alcohol, you actually need more grain in order to make that beer, and that means more expense and therefore low profit. So what is the optimal amount of alcohol that there should be in beer? So this was approach. Okay? Pure approach. This has very powerful thing. So he actually published under the name Student. Okay, he didn't publish under his own name, he published under a pen name. And that is now known as the student's D distribution or student's statistical significance. The one that we about here, this T distribution, this number that we defined here. Okay, so it actually turns out that this has advantages. So although so Fisher actually didn't like this economic element, he erased it from the from what he taught. But actually, you see that if you don't use it, you run into problems. And my last thing I'll talk about. So Merck is known as a large pharmaceutical company, third largest drug manufacturer in the US in 2005. Its painkiller Vioxx was first distributed in the US in 1999, and by 2003 it had been marketed in over 80 countries, bringing in $2.5 billion in revenue. But in 2003, a 73-year-old woman died unexpectedly of a heart attack while taking her prescribed Vioxx. Clinical in 2000 and in the Annals of Internal Medicine in 2003 reported that 5 patients taking Vioxx had suffered heart attacks during the trials, compared with 1 who were taking naproxen, and they concluded a difference that did not reach statistical significance. This is because Fisher had recommended that you use a fixed value of 0.05, that is 5%, for determining statistical significance. Okay, so they used that 5% and said therefore it did not reach statistical significance. The signal noise rise to this 5% significance that the Annals of Medicine, Internal Medicine uses as a strict cutoff for demarcating the significant from the insignificant. And Ziliak actually argues that you should not use a strict cutoff like this because that gives rise to all kinds of problems. As we can see here, Merck claimed there was no difference in the effects of the 2 pills. The article neglected to mention that in the same clinical trial, 3 additional takers of Vioxx, including the 73-year-old woman, suffered from heart attack. So actually, it was a total of 8 deaths rather than 5. So this is also a case of data suppression. So did they drop the 3 observations so as to get the statistical significance below that 5% level, and which allowed them to claim as 0 effect? If the Merck scientists could get the number of heart attacks down to 5, then they could claim to other scientists that the harmful effect wasn't there and was 0. That's basically, so you should use all of these statistical measures with a certain degree of caution. Okay, you have to use your head and not just a blind criterion in order to decide whether data are significant or not. And I have a couple of more slides. I won't go through those. Just deal with testing different kinds of hypotheses. When you have, so there's this F distribution and there's the Z distribution, the chi-squared value and things like that. So okay, I'll just stop here. And in case you have any questions, I know I ran a little bit over time, but I'm sorry about that. But we lost connection at a couple of places, a couple of points. So if you have any questions, you're welcome to ask them. Thank you for staying back longer than you should have. Thank you all. Sukant, yeah, Priyank, go ahead. Should I open the chat or let's see. I can't see the chat at this point. Let's if you can unmute yourself and ask the question. Yeah, okay, I can see the chat. Okay, is it on? Okay, There doesn't seem to be any questions in the chat. But somebody raised their hand. If you want to unmute, you can ask your question, or you can type it. Is this session going to be available again? Depends. Dr. Khurana, how much of it was lost? I can make the slides available, and you should be able to find from that. Yeah, Mohammed Awal, please ask your question.
Okay. Yes, sir. Good day to you all. Thank you for this wonderful session, sir. We really appreciate all your efforts. My question is regarding the statistical significance you raised issue on. So I don't know if someone is using a specific p-value. Let's say you are taking a p-value anything less than 0.05 as significant. So if we get that value less than 0.05, should we go ahead and report it as significant or not? If that's
so, if I go back to that slide. If I go back to that slide, yeah. So the argument is basically if the t value is less than the tabulated value of the t distribution, right? Then you can say that the data is accepted. The null hypothesis accepted with an error probability of this thing. So, and here this error probability is what you are using the 5% for. Okay. So the criterion is that if it is that with a probability of 5%, your null hypothesis is accepted. That means here there's a 5% probability that your data is, there's less percent probability that your data is coming from the null hypothesis. That means it's just coming from random. Okay. So the argument of the argument of Gosset and Ziliak is that it depends whether you should use 5% or some other cutoff, depends upon how significant, how on the size of your effect. Okay, if the size of your effect, in this case, the effect is that the patient died. Okay, so that's a pretty significant effect, rather than, let's say, you grew a mole or your hair fell off. Okay, that's a much less effect. So, and your tolerance, your tolerance will depend upon the importance or the impact of your phenomenon. So, will I swallow a drug which has 5% probability of killing me? No, I don't want to swallow a drug which has 5% probability of killing me, right? Unless I'm already dying. Let's say I'm dying of cancer, and if I swallow the drug, there's a 5% probability of it killing me, but 95% probability that I will live, then okay, I'll swallow the drug, right? But if it is, let's say, a drug to lose weight, I'm not going to swallow that if you just reassure me that there's less than 5% probability of your dying as a result of this drug, right? So it depends upon. So you should use common sense, in that. So that's what the argument is here. Okay.
okay. Thank you, sir. Thank you.
Okay. Yeah, I'm. So some
Sukumar?
of these. Yeah.
So I'm not a believer here, but since This is an interesting point that two ideas, whether the thing is significance versus hypothesis testing, you know it very well. They came from two opposing schools of thought,
Right.
one American, one
Right.
British, and now they've been
Mm-hmm.
fused together without everything fully making sense. So, to explaining that to
Yeah.
most people who are explaining that to people, especially after bachelor's or master's, where they used to just
Yeah.
putting a p-value. Uh,
Mhm.
so it is. I think maybe we should even have some other things on significance, even though this is more
Mhm.
bioinformatics thing. It's not really experimental data, so the some of the
Right.
p-values become less relevant.
Right.
But I think having a mini series, and I'll talk to you separately, even something else which can be a commercial thing, because most biologists don't understand statistics. So I think
Right.
maybe two, three of us teaming together to put up a proper course on Coursera or our platform will be useful. But for these
Mm-hmm.
people, we should put up something. Um,
Yeah, that's why I didn't spend too much time on the statistics because I thought it would get rather heavy. Uh,
yeah.
but those who are interested can contact me. I've given my email here. Or as you said, we can organize a special session specifically geared at people for whom this is, most relevant.
Because we are going to have three kinds of population. We
Mm-hmm.
have a dedicated bunch which is planning to go for PhD either in July or next year. There are exceptional people who already published planning to go this year. They may not do some good research, but we have people who will be here with us for 6 months to a year. Very dedicated bunch, and the number is going to be roughly around 100. And then we have people who will do something reasonably another 300, 400. And then we have around 2000 who are here to just go through some training, get a certificate, and leave, which is not a surprise and not a problem. We
Sure.
understand
Sure.
we don't take it away. So, of the people who want to go for a PhD, it will be a huge advantage to understand how these basic things of statistics evolved, what are the underlying assumptions, how they can be wrong. In fact, um, these are not from data science statistics background, but we will recruit few. And between you and me, Professor Sukumar, actually from Cold Spring Harbor, I should even find out if my boss is still alive or dead because he hasn't been seen online for the last 5 years.
Mm-hmm.
So there were two, three works on pure statistics that I had done, not AI.
Mm-hmm.
And they were sort of, the idea was to postpone them compared to our work on autism and group like locomotion. But he never came to it. And then when I had time, he just vanished. He went to Tsinghua University, which is China's leading university, as the dean of neuroscience and organizing thing, and I haven't found his trace. I don't know if he did something with Chinese government and he just vanished, or
Mm-hmm.
is he alive? More public without figuring out if he's still alive or not. So because he paid for my salary while I did those things. But they are interesting things on even conditional probability of things, which is very relevant for a lot of complex things that get consulting. And applying some statistical approach to it is not really fair. So I'll have a separate discussion with you. But I think
Sure.
your lecture brings forward some interesting points that we should organize some sessions with these people for the ones who are dedicated for PhD and deeper research. Okay, anyway, thanks a lot. It was an amazing session. If other people have questions, they can keep asking you. But I really enjoyed it.
Yeah.
Thanks a lot.
Yeah. So also, so the people who said, "Will this be available again?" The thing, you're planning to make the presentation video available on the YouTube channel, right? So
Yes, after some editing, because there've been a lot of
yeah.
glitches,
Yeah.
and
Sure.
able to edit it properly. Glitches we will make on YouTube. If not, we may request you to re-record it separately with no
Sure.
audience, with just Malvika, and then we upload it.
Okay. Okay. So if there's nothing else, then thank you, everyone. Yeah. Bye-bye.
Thank you very much, Professor Sukumar.
Okay.
Thank you.
Bye-bye.
Bye.